So I would like to start by thanking the organizers for having succeeded in organizing this meeting, and I also want to express my joy to see so many people here. It's an honor and a pleasure to introduce our next speaker, H.T. Yao. Yao really doesn't need an introduction, but let me nevertheless mention a few important facts about him. He grew up in Taiwan and got his bachelor degree from the National Taiwan University in 1981. Subsequently, he moved to the US to engage in graduate studies. He received his PhD from Princeton in 1987. His advisor was Elliot Lieb. In 84-85, I spent a sabbatical at Princeton just before Yao started to work with Elliot. Elliot and I worked on the stability of atoms in magnetic fields. We got stuck on certain aspects of this problem. Yao's first triumph, jointly with Michael Luss, was to solve the problem that we had left open. Lieb and Yao had an immensely successful collaboration on various ramifications of stability and instability of matter, Bose gases, the Chandrasekhar limit of stars, and other problems in the area of quantum many-body theory. After his stay at Princeton, Yao moved to the Courant Institute, where he started his career at NYU as an instructor and ended it as a full professor. At Courant, he started to work on, among other things, problems of deriving the equations of hydrodynamics from microscopic mechanics. He made a number of landmark contributions to this, as well as to many other aspects of understanding the effective dynamics of classical and quantum many-body systems. In 2003, Yao accepted a professorship at Stanford, and in 2006, he finally moved to Cambridge, where he has since been a professor of mathematics at Harvard. Yao's scientific oeuvre is very broad and very deep indeed. He is a world expert in the fields of many-body theory and effective dynamics. During the past 12 years, he has contributed amazing results to the theory of random matrices and has become a world leader in this field. A characteristic feature of Yao's scientific creativity is his unique ability to clarify problems in physics by using sophisticated methods of mathematics and to contribute to the development of pure mathematics by converting intuitions derived from physics into new mathematical insights. For his scientific triumphs, Yao has received a lot of recognition. Early in his career, he was a Sloan Foundation and a Packard Foundation Fellow. He won a MacArthur Fellowship in 2000. In the same year, he was awarded an Henri Poincaré Prize. In 2017, he received the Eisenbart Prize for Mathematics and Physics. And in 2001, he was elected to the American Academy of Arts and Sciences. In 2013, he became a member of the National Academy. He is the editor-in-chief of Communications in Mathematical Physics, certainly a very demanding and time-consuming job. I'm deeply indebted to Yao for having offered postdoctoral positions to several of my former PhD students, to the lasting benefit of those young people and to my personal joy. I now kindly ask Yao to present his lecture with the title Delocalization and Quantum Diffusion of Random Band Matrices in High Dimensions.
You can start now.
All right. So should I just start now?
Yes, please.
So I just started to present the talk now, but I don't see any audience. Hello?
Yeah, that's normal. Just start, please.
We are here.
Right. Okay. So I was starting to give a talk, and it's actually quite. I have never been so nervous about giving a talk, and this is quite strange setup. And okay, so now so let me start it. So So this is joint work with Feng Yang and Jun Yin. Yang is in UPenn and Yin is in UCLA. I mean, this is the main result of this talk is joint work with them, and but I have a lot of collaborators in the earlier works, and I will mention them during the talk. So this talk in the beginning, it will be the standard introduction of random metric theory, and I apologize for those of you who heard of this part before, and I have to go through the basic definitions. Right. So now we will start with a Gaussian random matrices. It's called a GOE, which is the n by n matrix, and then with I and j from 1 to n, and each one, because it's symmetric, real symmetric, and the variance 1 over n. And the reason we take variance 1 over n is for normalizations, and this can be, of course, if you change it, then it just changes the size of the system. And then, so it's a Gaussian, means also mean is 0 and the variance is 1 over n. And now, if you do the complex case, then the complex one is called the GUE. This means each Hij is complex variables. And so this is called the GUE, unitary ensemble. Another important one is something called a Wigner ensemble. Wigner ensemble is this Hij. You don't take this Hij as Gaussian, but they are just ID random variables, and it can be just plus minus 1, for examples. Now, the Wigner's motivation is come from the nuclear physics, and then of course you know the matrix. There are lots of Hamiltonian system. So in the Wigner's idea, he used random matrices to model the Hamiltonian complex quantum systems. And then the random matrix was also studied by Wishart and a long time, really long time ago. It's probably a century ago. And but nowadays you see so many random matrices are actually everywhere.
Can you hear me?
Because for example, like all this data science, and especially
can you hear me?
The current neural network, it's actually a large random matrix. Okay, so now the basic object of its eigenvalues and eigenvectors of this random matrix. This is what I'm want to say today. And so I order the eigenvalues lambda 1 to lambda n, and in the decreasing order. And then the Wigner semicircle law is given by this the eigenvalue density is given by the semicircle law of Wigner. And but on the other hand, the eigenvalue density it's not verifying information. If you want to go to the much more detail, you can see the distance. If you take the eigenvalue, you magnify it, you find the typical spacing is 1 over n. And the reason typical spacing 1 over n is simple because your eigenvalues, you have n eigenvalues. So then in between -2 and 2, and so the typical spacing is 1 over n. And then there was the calculation says the correlation functions at 2 energy, the correlation function at 2 energy and with separation x1 and x2 over n, then it's given by this so-called sine kernel. And this was a calculation by Golding-Mehta. And then this is for the GUE case, and for the GOE, for a real symmetric case, there's also another formula. It's much more complicated, and this formula can be turned into probability distribution for the eigenvalue gap, and which was and the Wigner was care about. So in the Gaussian case, these can all be computed. Now the Wigner has a grand visions, and his grand vision is this random matrix statistics. So his grand vision is actually here. is the local spectral statistics of highly correlated systems. The quantum systems are given by random matrix statistics. And then you use a GOE or GUE depending on which symmetry class you want to study. In other words, what Wigner was trying to say is that random matrix statistics are the new universal laws for highly correlated systems. And this is in contrast to the Poisson statistics for the independent random variables. Now, this idea Wigner was in the 1950s, and actually sometime around the time I was born, actually. And so I think some of this is, and then in the late 1950s, but then a simple question people ask is, suppose you take this Wigner ensemble, because the Wigner ensembles, the Hij are independent, but not Gaussian. So if Hij are independent, but not Gaussian, but do we know that these local eigenvalue statistics are given by the one with the Gaussian ensembles? And so in other words, whether the probability distribution of this gap distribution of the Wigner ensemble is the same as the GOE or GUE, depending on the case, the symmetry class. And then, so this was called, later on, this was called the Universality Conjecture. This was with the name Wigner, Dyson, and Mehta. And so this was, for quite some time, we didn't know the answer, but in the past 10 to 15 years, so that this conjecture was fully solved, and there was some extension of this. So this was about the eigenvalue part of the story. By the way, in this talk, I will mainly focus on because I want to explain you some of the more technical parts. So lots of reference and lots of names on the slide. I will not. I will just leave it on the slide, and you can see it, but I will probably just go a bit faster and focus on the mathematics part of the story. Okay. So now, so besides the eigenvalues, and then there's eigenvector. Now the eigenvector, we denote eigenvector by lambda 1 to lambda n. And then we also normalize in L2, standard eigenvector normalization to eigenvector in L2. And so now we have eigenvector U1 to UN. Now, so around the time of, actually the first work I did with Erdős and Schlein on this subject is to prove this semicircle law in local scale, and also the important thing is to prove this delocalization estimate of the eigenvector. So now this eigenvector delocalization estimate says because each eigenvector, so you take eigenvector J, and now this, so it's a component A, and now so we prove that the maxima in the L infinity norm of the eigenvector is close to n to the minus 1. Because n to the minus 1 is the best possible, because now because you normalize in L2, so each one it should be n to the minus 1, it's the biggest possible. But then we have some error, we leave some errors. And nowadays people can do this extremely precisely. I think the correction, the best possible is n minus 1 log n to this certain power, and so there are a lot of work I didn't mention here. So this n to the minus 1 plus epsilon right now is not the best possible. So there are very, very, very precise results about what's the correction in the n to the minus 1. These log n corrections for the but for the purpose of this lecture, we don't really aiming to get the best possible estimate for the eigenvector. So I will just leave it here, this n to the minus 1. The other thing I want to mention quickly, this was not exactly we are trying to do here, but it's quite related. Is the concept called the quantum unique ergodicity. The quantum unique ergodicity in the beginning is formulated by Rudnick and Sarnak, and this is for the eigenvector in the Riemannian manifold. And roughly speaking, you want to say the eigenvector is become completely flat. So in other words, this n to the minus 1, you want to say that if you take each component, it's n to the minus 1 times n, you subtract by 1. And then you take an average. Once you take an average, then you want to say that this average is small. So this means that the eigenvector, even though they are, it's the size around n to the minus 1 and they are up and down, but on the average, it will become completely flat. And this was called, we call this, we prove this in high probability. So this is with high probability. So let me use the high. So with high probability, this is correct. High probability means n to the minus any power. And this was called a probabilistic QE. And it was done in the beginning with the Bourget and also the in-join. And so we did prove this. And now there are many other works about this QE, and now there are some recent extension, and they have done things a lot stronger than what we proved previously. And but again, this is not the focus I want to talk about today, so I will just leave it here. Now, so it's clear that for the Wigner ensembles, Wigner matrices.
Sorry to interrupt. Could you please go full screen so we can see the slides better on site?
Sorry, you want me to go what?
Full screen with your presentation.
Full screen?
Mm-hmm.
Well, I'm in full screen. Okay, so let me do this. Is this better?
Yeah, now, much better now. Thank you very much. You can continue.
Okay. All right, so sorry. Okay, so all right, and then so this is this is the probability QE. So let me repeat. So about this page, and about this page is let me just show you slightly. Yeah. Okay. So so this we prove this delocalizations of eigenvectors, and then there's another concept called the QE. But all these are for the Wigner matrices. So the QE means the eigenvector, even though they are up and down. So you can think about eigenvector. The eigenvector profile, it can be like that. It can be like this. But on the other hand, if you look at big scale, it's actually you think about it in big scale, it's actually flat, and so that's what we prove for the eigenvector. All right. So now, and these are all proved in high probability because the whole thing is random anyway, random matrices. And now there are many other works, and the extension of this result about Wigner ensembles to many mean field models, and quite a lot of them. And you can consider the sparse case, and there are sparsity, and consider the Erdős-Renyi graphs. You can consider the correlated case, and you can do the general correlated case, or you can just with a correlated case with a more special structure like a D-regular graph, and also there are lots of models A plus B with B one of these, and A is another deterministic, and there are many other cases. So and you can see there are huge amount of besides the name I mentioned previously, there are lots of people, especially Jiayang Huang. He did a lot on the D-regular graph, and Jiayang Huang and Bauer Schmidt, anti-North. And then, but what I want to focus today is not about this this extension of Wigner ensemble. I want to focus on one thing is what about the problem is not mean field. If it's not mean field, because this is the whole point, we model the physics system by mean field type models. But the question is, the fundamental question is why this physical system, which are typically short range interaction and can be modeled by mean field models, which essentially they are interacting with infinite distance. So the standard models for the non-mean field models is random Schrodinger equation, random Schrodinger operator. This is Anderson models, and the other one is this random band matrices, and which was considered as a simpler model than the Anderson model. Okay, so so to me, the basic question here, the basic question in all the Wegener's visions is this a very, very simple question. Now, the question is why the mean field Wegener ensembles? We take a mean field, a GOE or GUE. Okay. Now, why this will model non-mean field systems? Non-mean field system is all the physical system are non-mean field. And why they, well, I cannot say all, but essentially all. So why this typical short range physical system can be modeled by the mean field Wegener ensembles. Now, there was two standard, or maybe one can call it the famous conjecture, is this Berry-Talbot is Poisson statistics for integrable dynamics, and then for the quantum chaos conjecture for chaotic dynamics, then you believe that you will get the GOE statistics if you look at Laplace operator in the domain. All right, so I won't go into any detail of this, but the upshot is the delocalizations and the random matrix statistics, it seems to be always happen at the same time. Okay, now let's go to the Anderson model. And the Anderson model, so you take a minus Laplace operator on the ZD on the lattice, and then you take a via independent random potentials on each lattice site. Now, there are two regions we are interested in. One is these localizations, and then in localization you get a Poisson statistics. This is for lambda large, and this was proved by Floric Spencer in a landmark work, and also the Poisson statistics was done by Minami and so on. And then there are also different proof later on by Eisman and Molchanov, and also has some other extensions. And but on the other hand, if you talk about the Anderson model, and then if you ask a question about delocalizations, there are actually essentially no result on the lattice. And then there are results on the graphs, on the tree graphs and so on. And so, but this is not really the original problem. And the other direction is instead of consider a stationary random object, you consider a dynamical thermal with interacting with phonons, and they look and Jörg Fröhlich, they did a lot of this, but this is time-dependent environments, and it's not what we are trying to address today. So about this random Schrodinger operator, actually the delocalization has very, very few results. And now we want to do an easier case. Actually, this was considered as it captured the essential ingredient of the Anderson model, but still it's not a mean field model. It's the so-called band matrix. Now the band matrix is a random, you can take it, it's a random matrix. But on the other hand, this random matrix is the variance. Now first of all, I want to label the matrix I and J. Usually we use a metric label I and J. But now the I and J are latticized on ZD. So I and J are latticized on ZD. This is very important, I and J. They are latticized on ZD. And on the other hand, now the variance of the HXY, of the variance of the metric element in H here, is given by something called SXY. And this SXY will be zeros outside a range W. And then, so you can take a Schwartz function or any function with complex support, and then you give a variance profile. Now this variance profile is very important. That if you sum over the row of columns, then you will equal to 1. So this is normalization we are taking. Now this one, the reason this one is not mean field is because that except a distance W, then outside the metrics are really exactly 0. So this means the interaction it's almost short range, because depending on what's the size of the W. If W is finite, then it's exactly a short range, and if W is slightly goes to infinity with L, and it's still nearly short range. All right, so this is called the band matrix, and the band matrix. So this is what I say. The band matrix is not mean field, and because all right, just say now for the band matrix, and the following result is known. So if you consider the green functions, gxx, this is h minus z, and you can take x and xy. It's also okay. You take eigenvector and then square them and divide by eigenvalues minus z, and so this was the standard expression. And now, if you consider the trace, so this is the trace of the green function divided by 1 over n. You call this m of n. And now, the theorem says this m of n will converge to this m of n. It actually will converge to the semicircle law. Now you converge to a semicircle law is given by the Rho SC, and if you take its Stiegler transform, the Stiegler transform of the semicircle law called MSC, so this m of n is going to converge to MSC. Now MSC is it can be computed explicitly because the spatial case, I mean the explicit formula is not important. So the theorem one has, we prove is if you look at green functions, and then you find it's in the delta xy, in the diagonal term we go to MSC, but in the off diagonal term it's actually, so the error of this with the difference between the green function and the diagonal matrix with MSC of z as the diagonal elements is 1 over square root of eta divided by w to the d. Is this one. So this is the error term. But this one, because this error term, so this means that it's only meaningful if eta is bigger than w to the minus d. Otherwise the numerator would become quite small, and the whole thing, the right hand side become very large, and then the theorem is sort of empty. But the important thing is this eta. This eta has to be, eta is actually quite large. I mean, well, eta is go to 0, but it's go to 0 with w to the minus d. Now, I want to mention that we typically view the eta, the imaginary part. So what is the eta? So I want to say, so your z, this complex variable z in the random matrix E plus I eta, and the eta is imaginary part, and eta is correspond to the inverse of the time in the unitary kernel. So you want to think about eta as a T inverse, but I mean this is just analog. It's a it's a conjugate variables, and so so you should understand this way. Now you also know that the green function will becomes highly unstable because if eta is less than 1 over n, and the reason is because you can see that you have lambda j minus z, and if eta is less than 1 over n, then your energy E will start to see the lambda j, because lambda j is the singularity of this of the E. So if you take eight, for example, if you take eta equals 0, then you clearly have a singularity at lambda j. And on the other hand, if eta becomes so small, then your singularity becomes quite explicit. And if eta is large, then you start to, this will be average out. So but eta less than 1/n is a threshold that you have a stable behavior. Below that, then you start to see that each. So let me just. Especially you have a lambda j here, and here. So you can see that your green function will have some sort of data functions behavior here and here, and the size of this is really eta. Okay. And now you can see that if eta is large, is bigger than this space, and then it becomes it becomes more like that. So if this eta is large, it's much bigger than 1/n. Okay. So so now so we are not very happy with not with this result because this restriction on eta, and our goal is really to go take eta all the way to 1/n if possible. And now now there's a conjecture called the quantum diffusion conjecture, and it says actually the off diagonal of the band matrix here. Oh, sorry. So the off diagonal of the band matrix, and this is off diagonal band matrix, and you take absolute value is squared, it's going to become something called the theta xy of z, and this theta xy of z is the m of semicircle of z squared times s. S is this variance matrix S, and 1 minus m semicircle of z squared of S. And this matrix is and gxy of z squared, they have a similar behavior. And this is correct for eta all the way up to n minus 1. So this is I don't think any I don't, well, this was so I don't know how to attribute this conjecture to who formulated, but it was a belief that the quantum mechanics, if you take in the Rayner-Schrödinger case, if you take a gxy square, then it will become diffusive, and that's why it's called a quantum diffusion conjecture. And then in the case of the band matrix, then, and after some time, it was there was some consensus that it would be behaving like this. And this was also, one also see this kind of behavior in some of our earlier works. And now the question is now, what's the behavior of this theta? The theta behavior, the behavior of theta, because S has a range W, and so it looks like it's a Laplace operator with a mass term eta. So the W square is correspond to the range of S. And then because this M square is 1 minus eta, so then the 1 will get canceled, and then it looks like eta minus the W square times Laplace operator. And now if you look at this guy, if you look at this object, if you look at this one, now we call it the B of eta. This is really a random walk, the kernel of random walk, and the green function of random walk, and then with time eta inverse. So this B eta xy, so we call this B eta xy, is a green function of random walk at the scale W and at the time eta inverse. So this was the quantum diffusion conjecture, and this is quite remarkable if you haven't seen it before, because it says this is equivalent. Okay, so maybe I would state the main result, and then I will come back to say more precise. Okay, so now, so here is the simulations, and in the simulation you find the theta and the t. Actually, they are quite close to each other, and So this is just, well, and this is just some simulations. And then, by the way, in this simulation, we are using the average over the green function. This is slightly more stable object, and we use this a lot. And from this T, we also can get back information of the G, okay? Even though they are slightly different. Now, now this kernel, this B eta xy, this kernel is random walk up to at time eta minus 1. And now you can compute this kernel. So I want to say, for example, if you look at it, because if you look at this kernel, it's really this is the Ukawa. I think this is the particle with this is non-relativistic particle with mass eta. So if you look at its decay in X, it's actually go like X to the D minus 2. So in dimension D, it's a D minus 2 here. And then you have a cutoff of X at W. So this dimension D bigger than or equal to 3. And this is for eta bigger than the shortest time W over L squared. And now what's the shortest time? So shortest time is, if you take a random walk, and so if you take, so now, just a second. So if you take a random walk in a cuboid size L, and now you start from the origin here, and then you ask yourself, now what's the time this random walk can reach the boundary? So random walk to reach the time at the boundary, of course, the time is L squared. So if you distance L, you need time L squared. You need time L squared to reach the boundary. Now this time L squared, and then why? This is called the shortest time. So shortest time is really just random walk of a size L to reach a boundary. And now we divide by W squared because everything in the band matrix, you should view that there's a scaling of W, and so the W is really the smallest scale in some sense, and so it's really L divided by W squared. So shortest time is really just this the time of this diffusion to reach the boundary. And now you can compute that this kernel. So if eta is bigger than W over L squared, if eta is W, then it's just like 1 over X to D minus 2. And otherwise, if it's even smaller, then you reach the boundary, and then there will be once you reach the boundary, so there was a backward scattering come back. So then you also have some inference coming back, and so there's another 1 over an eta terms in the. But this we will not talk about this the eta less than W over L squared. So there was a view of if you will get complete delocalization if the time you can control your green function is bigger than shortest time, because once you can reach the boundary, this means your information can propagate, and this is really the delocalizations. So it's all about. So if one formula this, so then you find that the typical inverse of the eigenvalue gap, which is n inverse to the inverse, so is n. So then the n is bigger than W, the shortest time. Sorry. So the n bigger than the shortest time. This is really the condition of the delocalizations. And now, if you look at this condition, now n is L to the D. So you write this n to L to the D, and then you find this L D 2 minus D is less than W squared. Then this will becomes the exact same condition. And you can see that if D has to be bigger than 2 in order this exponent to be negative, so D bigger than 2, you will get the delocalization for any large W independent of L. And now this also tells you that D equal to 1, the delocalization transition is W equal to square root of L. So today I'm going to focus on high dimension. So this one dimension, I will not say much. Actually, I will not say anything at all actually about this D equal to 1. So the result we have is the following. It's if you take dimension d bigger than 8, and the w is L to the delta. So this delta is any small number. So of course you would like to do what you would like to do is w is large independent of L, but right now we can do this w is as small as any L to the power as possible. You take any energy E in the bulk because at the edge, if you work on random matching, at the edge you typically need more work, and so we just want to focus on a simple case. And then your z is E plus I eta, and then you get the following. Then you find that for any partial integer m, and any xy belong to the torus z to the d torus L, expectation of gxy squared is given by this formula. So this one, you can see that it's almost the same as what we previously wrote, this conjecture, except there's a correction term. So maybe let me try to emphasize there's a correction. So the only difference is there's a correction term here. So the previous we thought that it's going to behave like 1 minus m squared s times m squared. Oh, sorry, I forgot s here. I forgot an s here. Anyway, it didn't matter. So I forgot s here. So, but then there's actually a correction term sigma m here, and this energy renormalization term is going. There's a term here, and then the error term is quite tiny. Error term is tiny here. So this with a tiny error term here. So there's a tiny error term, and then we can do this for 8 up to the thousandth time. 8 is w 2 plus epsilon divided by L squared. So this means the result hold up to the thousandth time, and so that's why we're going to have some delocalization estimate. Of course, this theorem, but not right now. This is oversimplified, and if you read the paper, there's some other error term I didn't write here. Now, the important thing is what is sigma m. This sigma m is actually a summation of m from 4 to m, and this lower order term actually is 0, and you start from n equal to 4. I mean, this n, don't worry about 4 because they don't have n minus 2, and so anyway, it's something. It's m is integer, and then for each integer there's a term, and each term has an order. So it's a summation of each term has an order w to the minus n over 2, a minus 2 times d divided by 2. So it's getting smaller and smaller. And then besides it getting smaller and smaller, it's very important, it satisfies cancellation properties. So cancellation property says if you sum over x, if you take this kernel, and this epsilon is a kernel 0x, if you sum over x, then this term looks good. If you sum over x, then it becomes even smaller. If after you multiply w n minus 2 d over 2, because to compensate it's a linear, it's a scaling size, it becomes even smaller because there's another after the sum, there's actual factor eta appear here. And this is the energy renormalization terms properties. Okay, so for the rest about, I think I have about 20 minutes, and I will explain how this result is correct, and what's the idea to prove this. And then now one consequence of this self-energy renormalizations is the following. It's in the, if you look at the Fourier space, and then a corollary is if you take a green function in the Fourier space. So here is if you take a green function in the Fourier space here, if you do the Fourier transform, it starts to have a characteristic p-square behavior. So you see that there's a p-square here. But then the diffusion coefficient it's actually quite complicated. One can compute this from this sigma m, but it's quite complicated calculations. And so, but this is something in principle you can obtain. And so if you take the point of view that the green function and the unitary evolution are sort of roughly about the same thing. So our result roughly says the unitary evolutions will induce a random walk up to the shortest time. So this is really roughly says the random walk is up to the shortest time L squared over W squared. But of course, I have to admit we haven't done work on this unitary evolution, because even though green function and unity kernels are sort of about the same, but it's not quite. You want to go from one to the other one, still lots of work. And I also have to say that the theorem I mentioned was only proved that for the complex Gaussian band matrix. And then we can also do the real case, because the real case is, roughly speaking, the number of graphs we have to deal with is roughly double. And so we just wrote the simplest case, and because it's already very complicated, so we don't want to. This real symmetric case is not a problem. And then the general case, if you don't use the Gaussian, then you have to replace this so-called Gaussian integration by parts we are going to use by a cumulative expansion, and so you will see. So this is about the proof. Okay. Now about the delocalization. The delocalization, there's a precise estimate. Is if you take a maxima of the eigenvector and maxima over x and over the I index alpha, because we only work in the bulk, so you have to avoid the edges. Then it's a W squared times L minus 2. So you have L minus 2. So it goes to 0 with a size of 1 of L minus 2. But of course, what you want to get is L minus D. And for this, then there's a notion of weak delocalizations. So this weak delocalization, roughly speaking, we just say eigenvector exponential localized in the ball of radius L. I mean, don't look at this math expression. It's fairly complicated, and one can show that the density of such eigenvector actually go to 0. So the number of these divided by n go to 0, and there are some more estimate. I suggest that don't if you're interested, you can go to a paper to see the precise statement. But my feeling is. It's because one can do the eta up to the shortest time. So if you want to improve the eta, it's possible, and then eventually this L minus 2 will become L minus D, and to the best possible size in L. Okay. And now, so now I want to compare this with the previous work, and the previous works. I think the band matrix, the band matrix. Density of states that was computed by Distori and Spencer, but about the density of eigenvalues, and this is by a supersymmetric method. And then about the delocalizations, and sometimes also about these universalities of eigenvalues. There are lots of work in dimension d equal to 1. So if you look at dimension d equal to 1, there are lots of there are lots of work on delocalizations. And there are also so this d equal to 1, so it has lots of work. And then in the localization direction in d equal to 1, there are also work by the Schenkers. And so I'm not going to go do this, say this in all details. And there are truly a lot of people working on this. And this is just a small sample of reference. And also Shabina, they focus on eigenvalue the 2-point functions, limiting distributions. So limiting distribution of 2-point functions, and use a supersymmetric method. So the supersymmetric method always tied with it's actually, well, one can view this as a special class of complex band matrix. And So they can do the eigenvalue, these eigenvalues correlation functions, the 2-point functions. But I don't know if there's some statement about the delocalization, localization estimates. Okay, so now I want to mention there's some work about these quantum diffusions in the random Schrodinger case and also in the band case. So there's work by Erdős and North in the band case, and also earlier, quite a long time ago. So right now it's more than 20 years ago. I did something with Erdős and Samhofer, and this is really about random Schrodinger equations. And these random Schrodinger equations, but the time we can do is just t lambda minus 2 minus c, and c is minus 1/4. So roughly speaking, it's random. It's actually one proof is random walk up to the time t is lambda minus 2 minus c. And so in these models, you want to view that the effective time. So the effective time. The effective time is really t times lambda square. So this is lambda to the, let's say lambda to the minus 1/4. So you only go to the effective time. This effective time means that this number of collision of your random walk is lambda to the minus 1/4. So it's not that big. I mean, it's go to infinity with lambda. But so now, so let me just say, I have about 10 minutes. I just let me explain now why this kind of result it took so long to figure it out. Is because if you take random Schrodinger equations and then you take minus Laplace plus lambda v. So I just want to explain one thing. If you take minus Laplace operator and plus lambda v and minus z, now you do the expansion. You just expand it, and then you expand in the resolving expansion, and then you find there are lots of v's. Okay, so now because you're interested in lots of collisions, lots of random walk, so this means if you have if v appear n times, then later on if you compute a green function square, you're going to have an n factorial problem. And now this n factorial problem, so you have an n factorial problem due to Gaussian pair, and the important graph are only a very, very small percentage, the so-called ladder graph. So only the ladder graph, and then lots of other graphs are not important, so they are small due to oscillations. And now if you look at the number of graph is lambda to the minus 1/4 factorial, because the time is lambda minus 1/4. And now you can see that if lambda goes to 0, then there are lots of graphs. And so in our work, so we have to deal with this, but this number is large but still manageable. But if you want to do the same thing, go up to the starless time in a band matrix, then you have to deal with this many L square divided by W square. L square divided by W square. This many graph, and to deal with this many graph, it's essentially impossible. And so that's why we didn't really do the standard, do this kind of the standard expansion. I mean, of course, this standard expansion one can renormalize in a certain way, but this factorial problem will not go away. Okay, so now the idea of what we are doing is we are just doing some Gaussian integration by parts, and then try to organize the expansion in some different way. Now, because the time limit, I don't think I can tell you this Gaussian integration by parts in detail. I mean, roughly speaking, you take a green functions, and now you write this in the resolving expansion, and so there's h times g. And now I add the m. This m is m semicircle, so that just to renormalize it correctly, and then because there's some identity, well, it doesn't matter. So you get the important term is h times g term. So you have h times g and equal to g. So this is just the equation of the green functions. And now, for example, if you take green function square and you take expectation, and now this h is h times g here. I expand one of them, the other one is just stay with g bar. And now the h, because it's a Gaussian, this is Gaussian, you can do the Gaussian integration by parts. The s will appear, which is variance, and Gaussian integration by part, you would take a derivative on this guy. And now you carry out these derivative terms, and now you write this in the graphic expansions, and you will see a graph expansion like this. So this is a graphic expansion like this kind of thing. So this original graph is a gxy and g bar xy. This g and g bar here, g and g bar. And then you go to the right hand side with lots of this is s, and you still have a g and g bar, and then sometimes you can see that you still have a gxx here, and the gxx. You know the gxx is going to close to m, and so you subtract the m, and then you separate into different terms. And so you can see that some of these vertices will have some weight, and then you get a g here. So it's a complicated equations. It's a complicated relation. It's not really, expansion in our standard sense. So if you organize this a little bit, and remember we call the t is the average of green functions times the s. And now you find that you obtain the following relation. This is a t, actually it's more the expectation of t. So sorry, it's really, I hate this, but there's nothing I can do. So if you take the expectation of t, so there's expectation of t, it's going to have this equation. So this equation, you want to view this in the sense of high probability or expectation sense. So you're going to have a t here. But the important thing is it's not just the t. It's going to have a it's not just have a t. Your right hand side is also have a, we're going to have a t as well. And now because there's a t on the right hand side, so you can solve the t, and then. But now the trouble is this error term and fluctuation term is going to be magnified, because this one minus m squared s is the same as this random walk kernel b here. And this kernel b will have a size of, this kernel b will have a size of 1 over x minus y to the d minus 2. So this one over x y to d minus 2, this is not summable. So because this is not summable, so this fluctuation error term is going to become is going to be quite, it will be magnified. And then, so for a long time we have troubles. We don't understand what happens because this one is this one will introduce a factor L squared effectively, because you can see the x minus y to d minus 2. If you sum over y, you will introduce L squared. And so this means that this error term will become L squared larger, and then we have lots of troubles. Then of course this W help a little bit, but in the case W is tiny, then you don't have this, you have serious trouble. So the key idea is this error term, we can identify the main term in the error term. The main term in the error term is a self-energy renormalization term. And this self-energy renormalization term, it has a property that you can, it has a mean zero properties. So it's of the form of a second derivative. So the error term, the main error term, is of the form of second derivative. And because it's a second derivative, so there's two derivatives can do integration by parts acting on B. And once you're acting on B, the 1 over x to d minus 2 will becomes 1 over x minus y to the d. So after the two derivative, you're going to get 1 over x minus y to the power d. So if it's 1 over x y minus y to the power d, our trouble is already solved, because then we don't have a troubles of L squared troubles. But now the question is why? How do we know the self-energy term is a second derivative term? This is because this is what's important is because now we say that there is a sum zero properties. It's we prove that it's sum zero and it's a symmetric. So any function f has sum zero and symmetric. So now if you look at it, for example, if you look at its Fourier transform, and now you expand in the p, so the first term p equals 0 is just summation f of x is 0, and then the linear term is p times f of x times x, because f(x) is symmetric in x, so this term vanishes as well. So then you got all the p squared left, and this explains that it's a second derivative term. So you need a sum zero properties, and it's a symmetry. So now the question becomes, how do we prove that this sum zero properties? Yeah, I start at the yeah. Okay, all right. Okay, so so right now, so the proof is by induction process, and then this induction process, I will not have time to explain it, and so this by this induction process, we can prove that this sum zero property, and it's a very different idea compared with the standard expansion idea, and also so this the explanation of the why d bigger than a comes out. I will just skip it, and finally there are further questions which are quite obvious. The one is how to decrease the dimensions from d equal to 8. And the other one is how to decrease this eta L minus d, and finally how to extend this idea to the random Schrodinger equation. These are the three so the obvious question one would like to pursue, and so I will end my talk here. So thanks a lot. Thank you.
So I want to thank you for a very nice talk, and I appreciate that you try to explain the ideas underlying your proofs, which is quite rare nowadays. So let's have questions. Martin.
You know, there's work by Eisenman and Tzer. Is the microphone on?
Yes.
Yes.
Eisenman and Tzer on delocalization on trees.
Yes.
Yeah, Cayley tree or beta lattice.
Yes. Yes.
Since you work in high dimension, I wondered whether you could connect in some way or other to that work. We believe that trees might be a good model to use in high dimension.
Yes.
So that's another more demanding question would be, can you say anything about a possible upper critical dimension? You know, in many parts of statistical physics, we have upper critical dimension, and there's this issue for the problem of delocalization, delocalization. Is there an upper critical dimension? But maybe that's too hard of a question to ask.
First of all, right now, we did everything on d bigger than or equal to 8. And one can lower the dimension a little bit, 7 or 6. And but I think there's a quite, there's a good chance that one can go to up to 4 dimensions, and the heuristic seems to suggest that's correct. And to a dimension 3, it seems there are some, there are works, quite a lot of work has to be done. So I don't really exactly know what's happening. And this because right now, even this dimension 7, 6 and, 5, 4 and so on, it's a lot of work, and so it's hard for me to comment on what's going on in this upper critical dimension. And for the beta lattice, for the tree graph, it's of course, I mean, if one apply the method to the tree graph, and I expect that one can we can prove similar results in the tree graph. But on the other hand, for the tree graph, because the tree has very different property compared with the standard lattice, the size of boundary and so. So I never really tried it and never seen it, what's going on there. But on the other hand, there's also work on a deregular graph. If you take a deregular graph, then the deregular graph base is a tree graph with some triangles and so on. And so it's slightly more complicated than tree graph. Then one can also do a lot on the deregular graph. In the case of deregular graph, there's also a proof of delocalizations up to d bigger than or equal to 3. So, but on the other hand, if you really ask me that whether I can reproduce, so we definitely have not even think about whether we can reproduce all the results of Eisenman and Simone, Wasa has done. And it was, they are doing things going to quite different direction in some sense. And so all I can say is I expect the method, what we are doing can work there, but what they prove, I think, is quite a bit different from our result. Yes?
I thought there was a question back there, no? Somebody raised a hand. Apparently not. Any further questions in the hall? Oh, Benjamin.
Hi, maybe I'll ask a very quick question. Can you briefly say where is this 6th dimension or 8th dimension coming from? I mean, I noticed you.
Oh, yes. All right. Yes. So the idea is the following. So now if you take a green function gxy, and the green function square is go like 1 over x minus y to the, roughly speaking, 1 over x minus y to the d minus 2. This green function is square. So the green function square, when you integrate, there's L square factor. And this is a problem. And now, on the other hand, if you can deal with all this, every time you see gxy square, if you find this guy, you integrate over something, it's always against the sum zero object, then this problem, L square problem, is solved. So next one is gxy to the cube. Now, if you use gxy to the cube, then you find that it's d minus 3, d minus 2 divided by 2. So then you find d bigger than or equal to 6. And now, so this d bigger than or equal to 6 is if you can deal with all the graph, the gxy square in a precise way, and then the green function to the cube, then it's go to a 6. And then we got the 8 because there are some a little bit technical problems. So that's how the 6 comes out. And actually, if you can maintain the parity, they then try to say that the real very relevant one is the 4. Then if you have a gxy to the 4th power, then you will find a d bigger than or equal to 4. And now if you want to go to the 3, then this means this part you also have to deal with very, very precisely. And then one might be able to go to d equal to 3. So right now what we are basically, all our proof basically says the gxy square, you always integrate with respect to with respect to some zero kernels, and otherwise everything with a cube, then you use this condition, d bigger than or equal to 6, and 6, so we waste a little bit, it becomes 8.
Thank you. So,
Are there any further questions? Is there a chat?
no, online there is currently no question, so I think we can.
Well, if there are no further questions, I would like to thank Yao again for his interesting lecture.
Well, thanks, George. Thanks, everybody.